Welcome to the deep dive. Today, we're looking at something pretty cool, moving fast from sci-fi into, well, actual engineering. It's about putting artificial intelligence into small satellite missions.
Yeah, imagine these tiny spacecraft, not just collecting data, but actually thinking, making smart decisions way up there.
Exactly. And we've got a couple of key resources to help us unpack this. There's an article, AI on Small Satellites, Opportunities, Risks, and Benefits, and also a presentation by Frank Lavinia called Where No AI Has Gone Before.
hmm
Our goal today is simple: give you a really clear, insightful picture of this whole cutting-edge field without, drowning you in technical stuff.
And it really is a pivotal moment. That
Yes.
presentation, the Levy one, it makes this great comparison to the Apollo missions.
Oh, yeah.
Remember how shrinking computers down was this huge hardware revolution? It let us get to the moon.
Right. The Apollo guidance computer. Tiny processing power by today's standards, but revolutionary then.
Exactly. And now we're kind of seeing the same thing with AI on small satellites. It's like a compression of intelligence, you could say. It's poised to totally change how we use and explore space.
A compression of intelligence. I like that. It's not just a small step, it's a fundamental shift.
For sure.
Okay, so this deep dive isn't just about how neat AI in space sounds. We're going to dig into the really important stuff. The possibilities, yeah, but also the risks, the practical side of putting AI on these little spacecraft.
hmm
We want you to come away feeling like you really get it, have those aha moments, and definitely not feeling overwhelmed.
Sounds good. Where should we start?
Right, let's start with a really basic need, just knowing what's actually orbiting Earth. That brings us to Space Situational Awareness, SSA.
Oh, yes, SSA.
Yeah.
It's essentially tracking and understanding everything up there, functioning satellites, old rockets, and of course the big one, space debris.
Which is a growing problem.
A huge problem. And traditionally, we've done this with radar and telescopes on the ground, which works. But think about having sensors, smart sensors, actually in orbit.
Right, a different perspective.
Exactly. Small satellites with AI on board can give us unique views from up high, adding a whole new layer to what we see from the ground.
Okay, so how does AI specifically make that better? Our sources point to a few key things. First up, onboard object detection.
Right, so instead of beaming down tons of raw sensor data and analyzing it here, the AI does it right there on the satellite.
Using things like neural networks, computer vision.
Yeah, exactly. Neural networks are great at pattern recognition, and computer vision lets the satellite see and interpret images. So it can analyze sensor data, maybe optical images, and spot nearby objects against the stars, all in real time.
Real time. That sounds like the key benefit there. Much faster hazard awareness.
Much faster. Imagine if a small sat detects debris on a collision course. It could potentially alert operators or maybe even trigger an evasive maneuver way faster than waiting for ground analysis.
And you could have networks of these things, like CubeSats working together.
That's the idea. Collaborative scanning. A whole network of AI-enabled CubeSats could give us a much more complete, up-to-the-minute picture of orbital traffic. It's moving towards being proactive about managing space, not just reactive.
Okay, that's detection. Then the sources mention relative navigation and inspection. What's that about?
Think small inspector satellites. Guided by AI, they could autonomously get close to other objects, maybe another satellite, maybe something unknown, and monitor it safely.
Like checking for damage or seeing if a satellite is behaving strangely?
Precisely. The U.S. Air Force had an early experiment, Angels, that touched on this. But modern AI could really boost this capability. Autonomous proximity operations, damage checks, anomaly reporting, all without constant joystick control from Earth.
Which could be massive for future stuff like fixing satellites in orbit or refueling.
Absolutely. On-orbit servicing, debris removal. AI-driven precision and autonomy are pretty much essential for those kinds of delicate close-up maneuvers. It's a big leap in how we can actually interact with things in space.
And it gets even more connected with collaborative constellation tracking. This sounds like the detection idea, but scaled up?
Kind of. Imagine multiple small sats, all with AI, acting like a distributed sensor net. They talk to each other. If one spots something interesting, it can tell the others, hey, look over here.
And the AI helps put the pieces together.
Yeah, that's AI-based data fusion. It takes observations from multiple satellites, maybe each seeing things slightly differently, and merges them into one coherent picture. So you get a better, faster understanding of things like satellite maneuvers or collisions, or maybe where new debris just came from.
Which helps deal with the sheer amount of data, I guess. Ground systems must get overwhelmed.
They can, yeah. A distributed network like this offers better coverage, more persistent surveillance of what's becoming a very crowded environment.
Okay, so let's recap the benefits for SSA. We've got faster detection in orbit, quicker reactions to threats,
Right. Collision avoidance being a big one.
plus filtering data on board, like that ESA ASAT-1 mission you mentioned, filtering out cloudy Earth images, saves bandwidth.
Huge savings potential there. Send down the useful stuff, not the noise.
And finally, better coverage and constant monitoring through these coordinated swarms of AI small sats. Seems pretty powerful.
It is, but we also need to talk about the challenges and risks here. It's not all smooth sailing.
Right. Like, how accurate is this AI detection? Can we trust it?
That's a major question. False alarms are one worry, but even worse is missing a real threat. So, robust training with good data, rigorous testing, absolutely critical to build that trust and reliability.
And these are small satellites. Processing power is limited, right? Can they run complex AI quickly enough?
That's a constant balancing act. Compute constraints are real. You need optimized algorithms, maybe specialized hardware. And then for the collaborative stuff.
You need reliable communication between them.
Exactly. Reliable inter-satellite links, effective consensus algorithms so the AIs can actually agree and coordinate.
And ultimately, how much control do we hand over? Especially for safety stuff like dodging collisions.
That's the autonomy versus human oversight debate. It's crucial. We'll likely see a gradual approach. AI makes recommendations first, then maybe gets more authority as we gain confidence.
Okay, so AI is making the neighborhood watch in orbit smarter. But it's also changing how the satellites themselves work, right? Let's get into AI-driven onboard autonomy.
Yeah, this is about giving satellites more power to manage their own operations without needing constant step-by-step instructions from the ground.
Satellites already had some autonomy, didn't they? Like running schedules.
They did, basic stuff, but AI kicks it up several notches. It lets them make intelligent decisions, adapt their behavior based on what's actually happening in real time, based on their mission goals.
So less like following a rigid script, more like thinking on the fly.
Sort of, yeah. It's about adapting to the environment and the mission needs dynamically.
The sources highlight autonomous mission planning. How does that work?
AI algorithms can basically allow a satellite to plan its own activities. Say you have an Earth-observing CubeSat. AI could look at weather forecasts, sensor availability, mission priorities, and decide itself what targets to image next.
Instead of just following a preloaded list.
Exactly. NASA emphasizes this kind of true autonomy, especially for deep space missions where the communication lag is huge, and also for managing really large constellations. Too many satellites to micromanage individually.
That makes sense. It gives them flexibility to react to unexpected opportunities, like a sudden scientific event.
Precisely. Or maybe a sudden need for comms bandwidth in a certain area. An AI-powered satellite can be much more responsive and efficient, potentially getting more science or commercial value out of the mission.
Okay, what about reactive operations and fault management? Sounds like handling problems.
It is. AI can constantly monitor the satellite's health sensors, power levels, temperatures, you name it. If it detects an anomaly, something outside normal parameters.
Like a sensor glitching.
Yeah, or a sudden power drop. The AI could potentially diagnose it and take corrective action automatically. Maybe switch to a backup sensor or shed some non-essential load to save power.
Which would be much faster than ground controllers noticing, analyzing telemetry, and sending commands back up.
Much faster, and it reduces the workload on the ground significantly. Plus, catching a small issue early with AI could prevent it from becoming a mission-ending failure. It could really extend the operational life of satellites.
And just like with SSA, this can happen across multiple satellites. Distributed constellation coordination.
Yes, same principle, but applied to mission tasks. AI agents on different satellites communicating and collaborating to achieve a shared goal. NASA's Starling mission is a key example, testing this swarm coordination.
So you could have a swarm adapting its Earth observation coverage if one satellite has an issue, or doing a coordinated search.
Exactly. They could spread out to search an area, then maybe autonomously converge when one finds a target. This kind of coordinated swarm behavior unlocks really complex missions that would be almost impossible to manage traditionally.
Okay, the benefits of autonomy seem clear. Faster decisions, less reliance on ground control, lower costs, better resource use, enabling more complex missions.
Big upsides. But again, the flip side, the risks and challenges.
Right. How do you even verify and validate that the AI will always do the right thing, especially in space where anything can happen? That do no harm principle is key.
It's incredibly complex. Testing for every possible scenario is practically impossible. And just integrating complex AI software with the satellite hardware adds more potential points of failure.
Plus the compute limitations we already talked about for SSA, still a factor here.
Definitely. More sophisticated autonomy needs more processing power. So again, you need optimization, maybe specialized low-power AI chips.
And the ethical side. Letting a machine make potentially critical decisions autonomously, like maneuvers.
That's a big one. Safety responsibility. These are areas the space community is actively grappling with as autonomy increases.
Okay, so we've got smarter awareness, smarter operations. What about security? AI for cybersecurity and resilience. Is that becoming a bigger focus?
Hugely. As satellites get more networked, more software-driven, they become bigger targets. Cybersecurity isn't an afterthought anymore. It's essential. And AI can be a powerful tool here.
How so? First thing mentioned is anomaly and intrusion detection.
Right. Similar to fault detection, AI can monitor all sorts of system data logs, telemetry, network traffic, but specifically looking for patterns that suggest a cyber attack or unauthorized access.
So it learns what's normal for the satellite.
Exactly. And then it flags anything that deviates significantly in real time. It's like an onboard intrusion detection system, constantly vigilant.
And it might spot things a human analyst could miss in all that data.
That's the hope. Detecting subtle, sophisticated attacks early is crucial to stop them spreading, especially across a whole constellation.
And can AI do anything about a detected threat, like adaptive security responses?
Yes, that's the next step. If the AI detects jamming, for instance, it might autonomously tell the radio to hop to a different frequency. Or if it detects malware trying to run, it might isolate that process or try to reconfigure software to block it.
All without waiting for commands from Earth.
Potentially, yes. Which is incredibly valuable if ground communication is disrupted or unavailable, maybe because of the attack itself. It builds resilience, makes it harder for attackers to succeed.
Interesting. The sources also mention secure and optimized communications, using AI for things like encryption.
Yeah, AI could potentially optimize encryption based on data sensitivity, or even explore things like behavioral biometrics, how an operator types, for instance, to add another layer of authentication beyond just passwords.
Adding more layers to the security onion.
Pretty much. The goal is to make sure data is protected and only authorized users are in control.
So the benefits for cyber. Real-time response, handling complex threats. AI is good at pattern spotting, resilience against attacks, and more confidence for operators.
Definitely. But like everything else, there are risks here too when you bring AI into security.
Such as, could the AI itself be a vulnerability?
That's a key concern mentioned in recent research. The AI software, being complex, might have its own bugs or vulnerabilities that attackers could exploit. We need AI-specific security testing.
And the detection systems, false positives, flagging legitimate activity as bad, or worse, false negatives missing a real attack.
Both are possible. Tuning these AI systems to be sensitive enough but not too sensitive is tricky. And running these security AIs takes power and processing resources.
Another hit on the already tight resource budget of a small sat.
Exactly. You have to balance the security benefit against the operational cost. And finally, you need to ensure the AI doesn't accidentally lock out legitimate ground controllers during an incident.
Right, the autonomous system takes action, but then humans can't get back in to fix things. Not good.
Definitely need clear protocols and overrides for that.
Okay, we've looked at SSA, autonomy, cybersecurity. Let's zoom out. What are the big overarching benefits and risks of putting AI on these small satellites?
Broadly, the benefits really cluster around speed, efficiency, and capability. Faster decisions, less data to downlink because of onboard processing like Sat1 showed us.
Right, the cloud filtering.
More autonomy in tricky comms environments.
Mm-hmm.
Being able to do more complex stuff onboard like analysis or planning. Potentially lower operational costs from reduced ground workload. And ultimately just getting more science or commercial value out of the mission.
Sounds great. But the risks we've touched on are significant too.
They are. The compute power and energy limits on small platforms are a fundamental challenge. Though, as you mentioned, new low-power AI chips like Google's Edge TPU, NVIDIA's Jetson, adapted for space, are helping.
And the space environment itself, radiation, reliability, especially for these advanced chips.
Critical. Making electronics, especially AI accelerators, tough enough for space is hard. That's where efforts like NASA's SC-Learn, focusing on fault tolerance, are so important.
Then there are the AI-specific risks. Security vulnerabilities in the AI itself, the fact that AI can sometimes be unpredictable.
Yeah,
How do you test for every possible space scenario?
you really can't, which is why robust design and maybe fallback modes are crucial. Plus, how do you update AI models in orbit? It's complex. And the whole legal and regulatory side of autonomous actions in space is still developing.
It's definitely a complex picture, lots of potential, lots of challenges.
It is. And actually deploying AI successfully means thinking through some very practical things.
Okay, let's get into those deployment considerations. First off, hardware. Choosing the right processor or accelerator.
Yeah, you've got options, each with trade-offs.
Mm.
Traditional rad-hard CPUs, tough, easier to program, but maybe slow for heavy AI.
Okay.
FPGAs, more flexible, better performance, reconfigurable. NASA's SpaceCube uses them. A good middle ground,
And then the dedicated AI accelerators.
like the Jetson or Edge TPU. Much higher AI performance, but need careful work to make them space-ready radiation tolerance, power draw. SC-Learn is tackling this. It's about balancing performance, power, and radiation hardness for your specific mission.
And power and heat are always big constraints on small sats, right? How does AI fit in?
It's tough. AI can be power hungry, so careful power budgeting is essential. Maybe only running the AI periodically, duty cycling, and heat. Getting rid of waste heat in a vacuum is hard. Needs clever thermal design so the chips don't cook themselves.
And making the AI models themselves more efficient seems vital. Model optimization.
Absolutely crucial. Techniques like quantization, using less precise numbers, or pruning, removing bits of the AI model that aren't essential compression, it all helps reduce the computing load and memory needed.
Plus using frameworks designed for this, like TensorFlow Lite.
Exactly. Edge AI frameworks like TensorFlow Lite or ONNX Runtime are built to run AI efficiently on resource-constrained devices like satellites. Lets you do real-time analysis on board without killing the system.
Then there's the decision. Do the AI task onboard or send data down for ground processing? Latency versus comms bandwidth.
It's a core mission design choice. If you need a fast reaction, or if the raw data volume is huge, onboard AI makes sense. Send down summaries, alerts, insights, not terabytes of raw sensor readings. But you need to define those decision pathways clearly in your mission plan.
What about the underlying software, the operating system, and how you structure things?
Reliability is everything. Often uses real-time operating systems, RTOS, or maybe specialized Linux versions. A key thing is software architecture. You want to isolate the AI tasks.
So if the AI crashes, it doesn't take the whole satellite with it.
Precisely. Use separate processors or software partitions, watchdog timers, safe modes, layers of protection.
And testing must be incredibly important before launch.
Simulation.
Oh, massively important. Extensive simulation using digital twins, highly accurate software models of the satellite and its environment is essential to check AI behavior. Field tests, too, like balloons or sounding rockets, help validate things in near-space conditions. Probably start small, right? Don't give the AI control of everything on mission 1.
Definitely an incremental approach. Use AI for less critical tasks first, gain flight heritage, build confidence, then gradually expand its role.
Lastly, regulations. If AI is making decisions about radio frequencies or maneuvers.
Yeah, it has to comply. AI, like cognitive radio, needs to respect spectrum rules from the SEC or ITU. Autonomous maneuvers need to fit within space traffic management guidelines as they evolve. You have to build those constraints into the AI's decision-making.
It's a lot to consider, but it's not just theoretical, right? Our sources mention real-world examples happening now.
Oh yeah, absolutely. Things are definitely moving. DARPA's Blackjack program, for example, with its Pit Boss system.
Right, that sounds intriguing.
It's about autonomous mission management for a military small-sat constellation, using commercial chips adapted for space, focusing on fusing data, making decisions, operating autonomously.
And on the civilian side, ESA's Borisat missions.
Great examples. ASAT-1 proved the concept of onboard AI for filtering Earth observation images, weeding out the cloudy ones. Showed real efficiency gains. ASAT-2 is flying more AI experiments. Clear business and science benefits demonstrated there.
NASA's doing swarm stuff too. The Starling experiment.
Yep, 4 CubeSats testing autonomous swarm coordination, AI for task scheduling, Inter-satellite communication,
Hmm.
figuring out how to make swarms work together intelligently.
And NASA's hardware work, SpaceCube and SC-Learn.
Key efforts to bring powerful, reliable computing and AI acceleration to small platforms, specifically tackling that radiation challenge.
Even the big aerospace companies are involved, Lockheed Martin.
Yeah, their SmartSat software-defined architecture, tested on missions like Pony Express, lets them try out AI apps, onboard image recognition, dynamic reprogramming in orbit, making satellites more flexible.
And it's not just governments and giants, universities, small companies.
Definitely. You see, universities doing crucial research, like University of Toronto testing radiation effects. And smaller specialized companies like Cognitive Space or Ubotica are popping up, offering AI integration expertise for space missions. It's a growing ecosystem.
So looking ahead, what's the future outlook? Where is this all heading? And what should people be thinking about?
Well, the clear trend is more AI. Expect proliferation of AI-enabled small-sat constellations. It's becoming a standard feature, not an exotic add-on.
Which means we'll need better hardware.
For sure. Continued advances in space-grade AI chips, rad-hardened, power-efficient, probably more modular designs so systems can be upgraded more easily.
And a bigger focus on making sure that AI is reliable and trustworthy.
Absolutely. More emphasis on robustness, verification, validation, new techniques, maybe explainable AI, industry testing standards. That's all likely coming.
Cybersecurity, too, built in from the start.
Has to be. Cybersecurity by design. As threats get smarter, defenses need to keep pace. Zero trust approaches, red teaming AI. It'll be standard practice.
And the rules and policies will need to catch up.
Inevitably. Policies for autonomous operations, space traffic management. Operators will need to engage proactively with policymakers.
We'll need more people who understand both fields, too, right? AI and aerospace?
Big time. Cross-disciplinary talent is key. And the sources recommend sticking with that incremental approach. Pilot missions. Demonstrators build confidence step by step.
And collaboration, sharing knowledge.
Crucial. It's a complex field. Sharing findings, partnering, that helps everyone move faster and tackle the common challenges like reliability and security.
So bringing this all home, AI on small satellites. It really feels transformative, like that compressing intelligence idea we started with.
It really does. The potential is huge. Smarter SSA, satellites that can operate much more independently, better cybersecurity, more efficiency.
But always balanced against those significant challenges. The compute and power limits, the harshness of space, security threats, the complexity and predictability issues,
Right.
and the practicalities of deployment.
Exactly. It's an ongoing journey, integrating AI into space tech. It needs that careful balance, embrace the innovation, but always prioritize safety and reliability.
Which brings us back to that presentation title where no AI has gone before. As AI pushes further out there, it makes you wonder, doesn't it? What new possibilities, but also what new responsibilities do you see for these increasingly smart companions we're putting in orbit?
That's definitely the question to ponder as this technology keeps advancing. What does it mean for our future in space?
Absolutely. Well, we hope this deep dive has given you a solid grasp of this exciting field. We definitely encourage you to check out the source materials for even more detail. Thanks for joining us.